The universe, as we know it, began about 13.8 billion years ago, in an event that would forever change the fabric of reality. Imagine everything we see today, all the stars, planets, and galaxies, squeezed into a tiny point, smaller than an atom, a singularity of immense density and temperature. Then, a massive explosion, the Big Bang, occurred, releasing an unimaginable amount of energy and setting the universe into motion. It wasn't like an explosion we see on Earth, with sound and fire. Instead, it was an expansion of space itself, a rapid stretching of the very fabric of the cosmos. This expansion flung energy and matter in all directions, creating the vast, ever-growing universe we are part of today. From that tiny point, the universe began to grow at an incredible rate, a process known as cosmic inflation, expanding faster than the speed of light. As it expanded, it cooled, and the energy began to transform into particles, the fundamental building blocks of matter. These particles would eventually come together to form the building blocks of stars, galaxies, planets, and even us, the complex beings capable of pondering our origins. The Big Bang is a foundational concept in astrophysics, explaining the origin of everything we observe in the universe, from the smallest particles to the largest galaxies. The early universe was a hot, dense soup of particles, a chaotic mix of energy and matter. Over millions of years, this soup started to cool and clump together due to gravity, forming the first structures in the universe. Imagine dropping food coloring into a bowl of water. It starts to spread out and form intricate patterns, much like how matter began to distribute itself in the early universe. Similarly, the universe's early ingredients began to coalesce under gravity's pull, forming the seeds of galaxies and stars. These clumps of matter became denser and hotter, eventually igniting to become the first stars, the luminous beacons of the early universe. These stars, much larger and hotter than our sun, were the furnaces where the first elements heavier than hydrogen and helium were forged, creating the building blocks for planets and life. The Big Bang set the stage for everything that followed, a cosmic symphony that continues to this day, with stars being born, galaxies colliding, and the universe expanding ever outward. After the first stars exploded in spectacular supernovae, they scattered essential elements like carbon, oxygen, and iron into the vast expanse of space. These elements, the fundamental building blocks of planets and life as we know it, are found everywhere in the universe, from the smallest grains of cosmic dust to the largest celestial bodies. They're in the air we breathe, the food we eat, and even in our own bodies, forming the very essence of our existence. These scattered elements, along with vast clouds of hydrogen and helium gas, coalesce to form enormous clouds known as nebulae. Nebulae are like giant cosmic kitchens where new stars and planetary systems are born, cooking up the ingredients for future celestial wonders. They are some of the most beautiful objects in the universe, glowing with vibrant colors from the light of newborn stars, painting the cosmos with their radiant hues. Within these swirling clouds of gas and dust, gravity continued to work its magic, pulling particles together with an invisible yet powerful force. Tiny dust particles, drawn together by this gravitational force, began to clump together like dust bunnies under a couch, forming larger and larger aggregates. Over millions of years, these clumps grew larger and larger, eventually forming the seeds of future planets known as planetesimals. These planetary seeds, or planetesimals, continued to attract more and more material through the relentless pull of gravity. They acted like cosmic vacuum cleaners, sweeping up the remaining gas and dust in their orbits, growing ever larger. As they grew larger, their gravitational pull increased, attracting even more material and growing into fully fledged planets, shaping the solar systems we see today. Gravity is a fundamental force in the universe, pulling objects towards each other. It's what keeps us grounded on Earth, what causes the moon to orbit the Earth, and what holds our solar system together. In the early solar system, gravity played a crucial role in shaping the planets. Imagine a giant disk of gas and dust swirling around the newly formed sun. As planetesimals moved through this disk, they interacted with each other and with the surrounding gas. Some collided and merged, growing larger. Others were flung out of the solar system entirely. Gravity caused the largest clumps of matter to collapse in on themselves, forming protostars. These protostars continued to gather material from the surrounding disk, growing hotter and denser until they ignited, nuclear fusion in their cores, becoming true stars like our Sun. As the Sun ignited, its powerful solar wind blew away the remaining gas and dust from the inner solar system. This wind, a stream of charged particles, cleared the way for the formation of the rocky planets we see today: Mercury, Venus, Earth, and Mars. Section 4, the early solar system, a chaotic dance. The early solar system was a chaotic and violent place with planetesimals constantly colliding and interacting. This period of intense bombardment, known as the Late Heavy Bombardment, lasted for hundreds of millions of years. Imagine a cosmic billiards game with planetesimals of all sizes careening off each other. These collisions were incredibly powerful, capable of shattering entire planets or even flipping them over. The Earth itself is thought to have been struck by a Mars-sized object early in its history, an impact that created the Moon. These collisions, while destructive, played a crucial role in shaping the solar system we see today. They helped to distribute water and other volatile compounds throughout the inner solar system. They also helped to shape the surfaces of the planets, creating mountains, valleys, and impact craters. As the solar system gradually calmed down, the planets settled into their current orbits. The gas giants, Jupiter and Saturn, with their enormous gravitational pull, helped to stabilize the outer solar system, preventing further planetary chaos. Section 5. Earth's fiery birth, a molten beginning. The story of our planet begins in a time of chaos and fire. The Earth, like the other planets in our solar system, formed from the gradual accumulation of dust and gas. These tiny particles, drifting through the vastness of space, began to coalesce under the force of gravity. As the Earth grew larger, its gravity increased, pulling in more and more material. This relentless pull of gravity drew in countless pieces of space debris, adding to the young planet's mass. This process released an immense amount of energy, heating the young planet from the inside out. The heat generated from these collisions and the decay of radioactive elements caused the Earth to glow with an intense fiery heat. Imagine a snowball rolling down a hill, gathering more snow as it goes. This analogy helps us understand how the Earth grew and heated up over time. As the snowball grows, so does its momentum and energy. Similarly, the early Earth gained more mass and energy as it continued to attract material from its surroundings. Similarly, the early Earth, bombarded by planetesimals and heated by radioactive decay, became a molten ball of rock. These constant impacts and internal heating transformed the planet into a seething, molten sphere. The intense heat melted the materials that made up Earth, causing them to separate into layers based on their density. This process, known as differentiation, was a critical step in the planet's development. The densest materials, like iron and nickel, sank to the center, forming the Earth's core. This core would become the heart of our planet, driving many of its internal processes. Lighter materials like silicates rose to the surface, forming the Earth's mantle and crust. These layers would eventually cool and solidify, creating the foundation for the continents and oceans. This process of differentiation was crucial for the development of Earth's internal structure and its magnetic field. Without this separation of materials, our planet would be very different today. The molten iron core, constantly churning, generates electric currents that create a protective magnetic field around the planet. This magnetic field is essential for maintaining the conditions necessary for life. This field shields us from harmful solar radiation, making life on Earth possible. Without it, our planet would be bombarded by deadly particles from the Sun, making it a much harsher place to live. Section 6. The cooling phase, oceans and atmosphere emerge. Over millions of years, the Earth began to cool. The surface solidified, forming the first continents. Volcanic activity was rampant, spewing gases and water vapor from the Earth's interior into the atmosphere. Imagine a pot of boiling water. As the water heats up, it turns into steam, filling the air with moisture. Similarly, the early Earth's volcanoes released vast amounts of gases, including water vapor, carbon dioxide, and nitrogen, forming the planet's first atmosphere. As the Earth continued to cool, the water vapor in the atmosphere condensed, forming clouds and eventually rain. Torrential rains fell upon the Earth's surface for millions of years, filling the first oceans. These early oceans were likely acidic and extremely hot, but they provided the cradle for life to emerge. The cooling of the Earth and the formation of oceans had a profound impact on the planet's climate. The oceans absorbed carbon dioxide from the atmosphere, reducing the greenhouse effect and allowing the planet to cool further. This set the stage for the emergence of life and the development of a more hospitable environment.